policies for limits of symmetric ideas.
Thank you very much, and thank you for being here. So, today I want to talk about the infinite polynomial ring. And it's a bit technical, but don't worry, I'll give you lots of examples. And this all works with a field of characteristics 0. So what is the infinite polynomial ring? You can think of it as the union of all finite polynomial rings. So I write this k big X, and X is kind of every variable indexed with I, and I big could be every positive natural number. All right. And first of all, maybe I should give some motivation. Why are we interested in this? Well, I think in this conference, we've seen lots of examples where we are interested in polynomials, symmetric tensors, and especially systems where we have more and more variables. And the idea is here to have some kind of top-down approach and look at these things all at once in like arbitrarily many variables. But the main problem is, of course, that if you look at infinitely many polynomials in arbitrarily many variables, well, you kind of really can't say anything about it because it's an infinite object, right? You can't do any computations, you can't get anything out of it. And as rightly, this is seen by the fact that our ring Kx is a non-Noetherian ring. So we can have ideas in there which are generated by infinitely many elements, or equivalently ascending chains of ideas like which have infinite length. All right. And now the solution here is to add symmetry to our problem. So, which was known by Cohen in 1967 and kind of discovered by Aschenbrenner and Hiller in 2007, is that if you look at ideas in our infinite polynomial ring, which are stable under permutation, so under action of an infinite symmetric group, which is nothing else than the union of all finite symmetric groups, then all such stable ideas, or I call them symmetric, follow the ascending chain convention, or equivalently, they are generated by finitely many elements up to this infinite permutations. All right. And now, again, it's a bit abstract, so I'll give you examples of such numbers. So, the most basic example, perhaps, is the example generated by just all our infinitely many variables. And of course, if you take some variables and permute the indices, you take some arbitrary permutation, you see that this ideal stays exactly the same, even on the level of generators. And if we think about this geometrically, then you can see that the vanishing in some infinite affine space, where points are just infinite sequences of numbers, and the only possible point vanishing on all variables is just the infinite zero sequence, right? It's just one point. And maybe some more interesting example is the coordinate axis example. And here, the generators are product of two variables, x, I, x, j, for distinct I and j. And now, if you look at the vanishing, you'll see that exactly all those points, which are sequences, that are everywhere zero, except for at most one point. So, again, because if you have 2 points which are non-zero, then you can just pick across some variables, multiply them, and this will be non-zero. And again, those are examples which we'll see throughout this talk, so kind of keep them in mind. And geometrically, you can think of this as kind of all coordinate axes in infinite time space. And the third example, which is a bit more mysterious and comes from the representation theory of the symmetric group, is a so-called stacked idea corresponding to a Hooke partition. And here, in a simple case, this is just you take 3 indices, and then you take the pairwise differences and the product of those. And geometrically, this is a bit more interesting space. So the vanishing of this ideal is just a space of sequences which attain at most 2 distinct values. So, for example, only 3 and 1.5, if you think about the rational numbers. All right. And because if you have only 2 different values, then one of these 2 differences will always be 0. And if you have 3 of them, well, you can just pick the corresponding 3, and then the differences will be 0. And here again, you can see that these are homogeneous and symmetric just on the level of generators. All right. Some simple examples out of the way. What is it I'm interested in? Well, what I want to understand is, because we have a homogeneous idea, I want to understand the degree D polynomials up to kind of up to relations in the ideal line. And I want to understand this for every degree D. And of course, the main tool to do this is the Hilbert series. I'll come back to this in a second. But the main problem and the main obstruction is looking at such graded degree D parts. They form vector space, but in general, it's an infinite dimensional vector space, because if you have some variable, let's say in degree 1, you have x1 in there, But then, because this is stable under the symmetric group, we also have x2, x3, x4 for every possible x. And if there are no relations, it's an infinite dimensional vector space, which is a problem, because always counting kind of infinity is a boring thing, right? And we really want to have some kind of hands-on numbers. And the solution here is to go down into the finite case. So what do? We look at the truncation to n variables. We take our homogeneous and symmetric value I, and we intersect it with a finite polynomial ring. And then we note this by In. And now note, because I was stable under the infinite symmetric group, our ideal In is stable under the finite symmetric. And they form a filtration. All right, now we have for each natural number n, we have exactly such an ideal In. And what can we do now? Well, we can look at the normal Hilbert series. So the usual Hilbert series, you've seen the Hilbert function was mentioned a couple of times. It just keeps track of the dimension of these vector spaces. So given such finite polynomial ring and some homogeneous ideal in there, then we can just write down the dimension of the degree degraded part. And then the Hilbert series is just a common power series where the coefficient of t to the d is exactly this dimension. It's just some finite number. Now, the nice part about this is a consequence of the Hilbert-Serre theorem. This is not some arbitrary power series. It is actually a rational function. So the quotient of two polynomials, meaning we can write this down with a finite amount of ink, do computations, really is like a finite object we can understand. And as a very basic example, we look at the coordinate axis truncated to two variables, and then what we portion out are all mixed terms. So what do we get? Well, we take a look at our ring, and the constants are always one-dimensional, and then in each other degree bigger than one, we only get unmixed terms, which is always two-dimensional. So we get the common power series 1 plus 2t plus 2t squared, and so on forever. And writing this as a rational function, this is just 1 plus 2t divided by 1 minus t. Right. It was just some basic complements. But now, the idea is to actually this concept to make it work for the infinite polynomial. And one solution is the equivariant Hilbert series developed by Nagel and Römer in 2017. And what they did is they said, well, we can truncate down our ideal I and our polynomial ring X to n variables. And here we have a finite number as the dimension. And we got the degree. So what do? We keep track of both numbers, the truncation and the degree d, and write this as a bivariate form in power series, just like this, right? Where the coefficient of s to the n t to the d is the graded dimension of the truncation to n and the degree d. And now, as it turns out, this is also a rational function. So looking at this, keeping track of both things, if you just restrict it to symmetry, you can find out that this is a rational. And again, this theorem works in a much more broader sense, but I have written it here like this, that it fits in the. All right. And now, yes,
you can play this game also without asking the sim ideals, right? Like,
you need some, like as I said, you need some condition. If you look at any arbitrary ideal, this does not work. So
I can write this thing.
Yes,
the work is that it's not a rational function.
It's not a rational function, exactly. It's not a rational function in general. But you can write this thing down. But it's just anything. I mean, I think you can get almost arbitrary things. But yeah, exactly. All right.
So what group is an equivariant with respect to the definition of the symmetric group?
What do you mean? This certainly doesn't appear here, you mean?
Yeah.
Oh. So, I mean, I think you can write this thing down for any ideal I, but it won't be a rational function. And you need it stable under the increasing monoid. So kind of your ideal I can be stable under the increasing variables, increasing indices in an injective way.
Yeah. But it can have to become bigger when you allow more variables.
Exactly. Yeah. And it also works for like a different action, but yeah, I mean, I don't want to go into too much detail, but it's really fascinating. I can see where this works and what does this. Okay. So this is kind of this special case. And what Colin and me wanted to do is we wanted to look at the representation theoretic side of this. Because if we look at the truncation to n and the degree d, we know that this is a vector space and it's stable under the action of the symmetric group in n elements, right? So this is just a representation of the symmetric group. And what can we do if we have some representation? We look at the isotypic decomposition. So we write as a direct sum of irreducible representations, denoted by lambda. And if you know a bit about the representation theory of the symmetric group, you know those are so-called Specht modules. And each irreducible representation appears a certain number of times, which we denote here by the multiplicities. And now, a priori, you don't know what happens if you increase n, but there's this very nice theory of stable representation. And I can show you here what happens. Well, look at the very basic example. We take the ideal, again, the coordinate axis ideal, and consider degree 2, and n for 2, 3, and 4. And if we take a look at this quotient, we see that we have here the trivial representation once, then here we have the alternating representation. And then if we increase our variable, our number of variables, so the truncation, we see that we still have the trivial representation, and we get some growing vector space, which is also an irreducible representation. And writing this down in terms of Specht modules, you see here we've got the trivial representation, and this number here grows. And this is just an integer function here. And what we have here is that we have representation corresponding to the position 1, 1, 2, 1, and 3, 1. So we see that the first entry grows. And this, what I've shown very crudely here, is not just some random thing that happens. There's a very deep theory behind this. And in general, it is those sequences of irreducible representations that we're interested in, where the first entry of the integer partition grows. So if we have some partition, which kind of, for each partition, we have an irreducible representation of the symmetric group, we are interested in the pellet partitions. So what are we doing? We are increasing, we pad some partition to n, meaning we increase the first entry such that the sum of entries is equal to n. And now looking at the irreducible representation Specht modules for pellet partitions, what we notice is that the dimension of these irreducible representations is unbounded from increasing n, except for the trivial representation, which is always one dimension. And so if we just increase the first entry. And this is kind of a problem, again, because we are interested in what happens in the limit. And again, just counting infinity is a boring thing. So how can we avoid this problem? What we're doing is we want to count multiplicities of the irreducible representation, which don't go to infinity in this representation. And we're starting with a trivial representation because it is always one dimension. Okay, so what can we do, which is also unique for the trivial representation? We take a look at our truncated quotient, and then we take a look at all invariant polynomials under the symmetric. And this forms a sub-ring, which is very nice. And in particular, it is still a graded ring. So what can we do? We can take a look at this ring, we can take a look at all invariant polynomials, and then we can take a look at all invariant polynomials, which is given D. And this forms a vector space. So we just count the dimension, and then n go to infinity. And now, this sequence here, for each n, is eventually constant. So this limit is actually a finite number which we can count, which is what we wanted to do. Because if you don't take the representation theoretical approach, this thing will always go to infinity, which is not what we want. Almost always. Okay, and why does this work? Well, it works because we can bound the invariant, this idea, the dimension, by the whole ring. And by the fundamental theorem of symmetric polynomials, we know that this thing here, the symmetric and the invariant ring, another symmetric group of a polynomial ring and variables, is just generated by the first n elementary symmetric polynomials. And taking the degree d here, this dimension does not grow for growing n if n is bigger than d. So this dimension always stabilizes. All right. And what do we do now? Having kind of extracted the symmetric dimension from the representation theoretical approach, we just use a normal Hilbert series approach. So we just count some subject space given by our representation theoretical. And then we take gradually form a power series t to the d with this symmetric dimension and write this down. And the question is this a rational function? And before I answer this, let me give you some examples. So writing it down for the most basic example, the trivial example, you see that the quotient here will always just be the constant, right? And then no matter what happens, if you take limits of 0, we'll always get 0. So as a common power series, we'll only ever just get 1. But this is good because this is also a normal Hilbert series of a point. We call that the vanishing idea of our eye is just the origin, and the Hilbert series of this is also 0, and we have no symmetry. So this is what we expect. And for a more interesting example, taking a look at the coordinate axis, we see that we have the constants, and then in each degree v, we quotient out our mixed terms. So we only have pure powers x, I, and d. And now, taking a look at invariance, we know that there's only one invariant up to multiplicity, namely the power sum, x1 to the d, x2 to the d, and so on after xn. So the vector space of invariant polynomials is always one-dimensional. We just get this very basic power sum, which is a rational function, 1 divided by 1 minus t. And note here that as vanishing, we have all the coordinate x of infinite time space, which are kind of the same under permutation of coordinates. And here we get the Hilbert series of just a normal line. So we see that kind of quotienting out symmetry, we actually get something sensible. There's a problem, however. And if you look at the zero idea, which is homogeneous and also invariant under permutation, so it should work. Well, we see that the symmetric Hilbert series is just a limit of the normal Hilbert series of the ring of symmetric polynomials. And this is given by this product of rational functions. And taking this in the limit, you just get the generating functions for integer partitions. And it's just given by this. It's an infinite product, and it cannot be written as a normal rational function. It's not a rational function. And this is the first problem. So here we have kind of a counterexample to rationality. But again, looking at some other examples which seem to be more complicated, for example, the Hochspecht idea, we can compute the symmetric Hilbert series, and we get that it is a rational function. So what is the answer to the question of rationality? Well, we do get it under a slight condition on the support. So given such a symmetric and homogeneous ideas, then we could show if we find an F such that one of its terms has a support which does not contain any other support, then the symmetric Hilbert series is a rational function. Okay, and let me explain this condition a bit more. So, for example, we have F here, which can be written as the sum of these three terms, where the support of the first term is just 1 and 2, the support of the second term is 1 and 4, and the support of the last term is 1, 2, 3, 4, because those are the variables which have non-zero support. And now we can either pick the first or the second term, and we see that the other two supports are not contained here, meaning any ideal I containing F will have a rational symmetric Hilbert series. This is a bit technical, but I can show that this is actually very general. Namely, if our ideal contains a monomial, this condition is trivially fulfilled because there is only one term. So symmetric Hilbert series is rational if I contains a monomial. Secondly, due to a result by Petro, we know that a symmetric and homogeneous idea which has generic coefficients in its support. So the coefficients are either 0 or kind of random. We do have a monomial. And thirdly, we know that this condition is sufficient but not necessary for rationality. So we find examples outside of it. All right. And now we can play the same game, not only for the coefficients of the invariant permutation, but actually for all irreducible representations. So instead of taking the symmetric dimensions, we just take the limit of stable of the multiplicities. And then under the exact same conditions, we get that the Hilbert series is rational, which we now call isotropic Hilbert series for the isotropic components. And this is just a straight up generalization because the case of the trivial representation recovers the symmetric Hilbert series. Okay. And now a quick word on the examples outside. Well, we can take a look at this space MR. This is the space of sequences which contain at most R distinct values. And the vanishing idea of M2 was our Hochspecht idea. So those are just Hochspecht ideas. Well, they are a very important family of ideas because we know that for any symmetric idea, the vanishing ideal I of MR is contained in the symmetric ideal of what R big enough. Most importantly, these vanishing ideas do not satisfy our condition for R bigger or equal to 2. So they are kind of the main family of counterexamples which are contained in any ideal eventually. But what Colin and me were able to do, we were able to actually just by hand compute the symmetric Hilbert series, and we found out that this is also a rational function. So it's a very complicated product of sums and so on, but it is a rational function. And which kind of gives us a whole family of examples outside of our condition. Okay. And now a quick recap, what did we see today, and then I'll come to my conclusion. We've seen the ordinary Hilbert series, which only works for fixed n. And then Nagel and Breloer developed the equivariant Hilbert series, which is a bivariate Hilbert series, kind of capturing all the graded pieces at once for all truncations n. But it's a bivariate series. It kind of only captures the general frame. And coordinately looked at the stable multiplicities of the representation. And here we had the simple case of the symmetric Hilbert series, keeping track of the invariant part, and then more generally, kind of for each irreducible representation, keeping track of the stable multiplicities or the limit multiplicities. And those were rational functions and the slides of our condition. So what we believe is, for simple examples, the symmetric Hilbert series behaves just like the usual Hilbert series, and our condition on rationality is quite strong, and all examples we could find outside of this condition we also have rationality, except for this kind of zero ideal. We do believe that the isotypic Hilbert series is actually a rational function for all homogeneous and non-zero symmetric. Okay. Thank you very much for listening. That was the talk.
So we have quite a few minutes for questions. Okay, and there's going to be plenty of time as well during the lunch break. Oh, we have one. Okay.
Yes, maybe it's a stupid question. At the beginning, you mentioned that you have this ideal which is stable, and this sharing chain of ideas.
Yes.
And that chain stabilizes. This is the first question. If it stabilizes, does it stabilize to something for which the quotient integrity as like finite dimension? So this be used also.
So there are kind of two chains we are looking at. I mean, this so-called sim infinity Noetherianity states that if we have an ascending chain of ideas in our infinite polynomial ring, which are all stable under this symmetric group, then this chain of ideas must eventually stabilize, which is kind of just Noetherianity in this specific case. And this is a different chain of ideas to these truncations. They never stabilize. They kind of grow and grow and grow.
Okay.
Yes. So those are different things, right? Those are not ideas of infinite polynomial ring, but you just truncate them down. Yes. Okay.
I don't know. So communities multiplicity is hard. Like an ideal you. But can you know this Hilbert series or what it is? Like they do things or the multiplicities I don't know. Like probably multiplicity that you cannot exactly.
I mean,
but that this series tells you something.
Yes. So what we managed to show is kind of that we have at most polynomial growth, right? I mean, we can take a look at here, right? So we have this sequence for each t, we have this limit of multiplicities. And what we managed to show is that in general, except for the zero case, we have at most polynomial growth. So we can bound the growth of these sequences, which is kind of, we also get in the normal Hilbert series, which is a nice thing. But yeah, in general, I mean, you would need to compute actually what the Hilbert series looks like, find out what it looks like in each step, or do a t-square piece.
Any question?
I mean, it's more like a direction. So there is like you talk about symmetric ring, like the rotational ring. There is like a GL side of this story, which connects a lot to Michael's talk from yesterday. This non-polynomial stuff, which is maybe some I don't know methods from this work. Let's say something about polynomials in that work or whatever.
Yes. Yeah. I mean, going back to the very beginning, you can ask like these questions. Take the infinite polynomial ring, and then you ask ideas stable under a certain kind of group. How do they behave? And I think there's also a theory for GL infinity.
Yeah, Jan Reisma has.
Yeah, exactly.
Things.
And yes, I don't know how this would work here, but I mean I haven't looked into this, but I guess it's an interesting question for how this would look like.
Let's thank the speaker again.